So as you can obviously clearly tell, this question consists of 4 emperor penguins being pulled across an icy surface by the mittened hand of a zookeeper or someone who's gently dragging our happy penguins across the ice to give them some food or something, certainly not to turn them into food for someone else. So, these 4 penguins, we know the masses of 3 of them. This guy has a mass of 12 kilograms. We don't know the mass of this penguin, 15 and 20. But we also know that the applied force on the whole group is 222. That's the tension in this first rope. We don't know anything about this rope. This rope has a tension of 111 newtons, and this one is unknown as well. And the question is, find the mass of the unknown penguin. So what do? Well, we start drawing free-body diagrams, right? We've done questions like this before where there's multiple things, and the first thing that we normally do is just draw a free-body diagram where the whole thing is one. So let's try that and see what happens. So I'll do that over here. If I draw a free-body diagram of the whole thing, they have a total mass of 47 plus m. So the mass is 47 plus m. Okay. There's an applied force of 222. You know, there's gravity on this thing, and there's the normal force on this thing. But they're going to balance out. And it's an icy surface, so we're just going to assume that there's no friction. So maybe I'll write that down. Let's say mu equals 0. If there was friction, it would become a slightly more tricky question. Be interesting though. Maybe next time. So the total free body diagram will look something like this. The positive direction I'm going to call to the right. X is to the right. Y is up. And I can see that the net force must be 222. And that's got to be equal to the mass, which is 47 plus m, times the acceleration, which I don't know, which is a. So I'll stop there because this is an equation with 2 unknowns. I can't solve it yet. I know that there's a bunch of different possible answers. So I'm going to have to look somewhere else for a little more information. Lots of possibilities. I could pick any of the penguins, but the problem with picking any one penguin is that I don't know anything. Like if I pick the 12 kilogram penguin, I don't know the tension here, and I don't know the acceleration. So I have 2 unknowns for this penguin, but they're not the same as these 2, so it would just make things more complicated. So why don't I try drawing the back 2? Because if I drew the back 2 penguins together as one free body diagram, then they'd have a mass of 12 plus m. They'd have a force of gravity, there'd be a normal force, but those would balance out again. And if I look at these 2 as one, the only external force is the tension in that middle rope, which is 111 newtons. X is to the right, Y is up, just like the other one. So I can say 111 minus nothing equals 12 plus m times a. And now I have 2 equations and 2 unknowns. So I know I can solve it. There's a lot of possible ways to do that. I think the easiest one will be to rearrange each for the acceleration. The acceleration is 111 over 12 plus m. And the acceleration over here is 222 over 47 plus m. They all have the same acceleration, assuming that the ropes don't stretch or anything. So putting these guys together, I can see that 111 equals 222. Sorry, 111 over 12 plus m equals 222 over 47 plus m. Cross multiply, this guy goes away, leaving with a 2. Cross multiply, we get 47 plus m equals 2 times 12 plus m. I'm going to do that in one step. 24 plus 2m. Move my m over here, move this over here. I get 47 minus 24 equals m. So the mass is going to be equal to 13 kilograms. Sorry, 23 kilograms. 47 minus 24. 34, 44, and 3 more. 23 kilograms. Now there are other ways of trying to do this. So, for instance, instead of drawing a free body diagram of the whole thing to start with, I could have drawn a free body diagram of just the front 2 penguins. And if I did that, I would have said 35, and I would have had a force of 222 to the right, I would have had a force of 111 to the left. And then I would have actually been able to find what this acceleration was. Right? It would have been 111 equals 35a. So acceleration is 111 over 35. So I could have found this number. The way I did it, the way I solved it, I didn't actually ever learn what the acceleration was. I just assumed it was the same for all the penguins. I could have, of course, though, drawn the 3-by diagram for the first two and gotten the acceleration, and then dropped the acceleration into this equation and found out. I would certainly have gotten the same answer, I hope. Some students can just look at this problem and know right away that the mass is 23, or almost right away. I'm not one of those people, but some people can. And knowing that the answer is 23, you should be able to look back at this and see why that makes sense. Look, these front two penguins have a mass, a combined mass of 35. 23 and 12 is also 35. Is that a coincidence that the front two penguins have the same mass as the back two penguins? No, it's not, and that's why some students recognize that. 222, 111. If this force is half this force, then half the mass must be in the back half of the train. Does that make sense? Double the force is required to double the acceleration. Sorry, double the force is required to keep the whole thing accelerating at the same rate. So half the mass must be in the front and half of it must be in the back. So some kids can just look at that and say, half the force, half the mass. And say, boom, 35 minus 12 is 23.